For those that don't know me, my name is Andrew Strong. I manage the business operations team at Correlation One and have been working closely with Alora and everyone on our team to organize this program over the last 5 weeks. The next session, what we are going to give everyone an opportunity to do is see some of the top projects from our programs. And so in addition to the training sessions and the networking, a really big piece of the Women's Summit program is capstone projects that every participant works on a small team. And a little bit of information about these projects before I introduce the first team. We structure these projects to simulate a real world experience. And so these projects are purposefully open-ended. We do not prescribe or predefine a specific challenge that each team should solve. Instead, we challenge them to come up with their own questions to ask of data in the real world and explore their own analyses and insights that might actually lead to potential change. These projects also require working in teams. Just like in the real world, we help the women in our program work in teams of 4 or 5 in a really short time period. And so they have a small amount of time to build something really special. And most importantly, they're meant to focus on real world impact and relevance. So they've explored some interesting, meaningful problems with data to uncover some new insights. We had 44 project teams, all submitted fantastic work, and we had a symposium this morning where they all had a chance to present. What we're going to do now is give the top 6 teams who were selected by their peers an opportunity to share their work with the full class. And so I will introduce now the first team. The first team is team number 8, who analyzed the effects of different containment measures on COVID-19. And I'll turn it over to that team's lead, Claudia Krawiecka. Claudia, the floor is yours.
Thank you everyone for joining our presentation. We hope you will enjoy it, and let's just start.
Our research was on the effects of containment measures on COVID-19. We're team 8, and a brief agenda of what we'll be going over today. First, we'll start with an introduction of just the topic, and then we'll go over the goals and objectives for our analysis, the EDA that we conducted, along with the stats analysis and machine learning. We'll wrap it up with the conclusion and key takeaways, and then end with Q&A. If you guys take the time to scan the QR code here, it actually opens up the PDF to this presentation, and you can follow along with us. So we'll give you a moment to do that. And for the introduction, it's been about 7 months since WHO declared the spread of COVID-19 as a global pandemic. And although everyone across the globe has been exposed to the same set of health threats, implications of this vary by country. This analysis aims to understand these variations. And just to introduce our team, we're a diverse team of PhD students and data scientists located across Europe and the US. My name is Sade.
My name is Claudia.
My name is Alina.
And my name is Velda.
And we'll be your presenters for the next 15 minutes. The goals and objectives for this analysis were basically to understand which governmental measures were the most effective in decreasing the number of COVID-19 cases, and then also to be able to predict the outcomes of enforcing specific measures and suggest strategies for mitigating the number of new cases. And I'll pass it off to Alina.
Hi, everyone. So in our project, we analyzed multiple factors that could potentially influence the spread of coronavirus in each country. For this, we integrated several heterogeneous data sources. First and foremost, we used the daily numbers of COVID cases and deaths per country that were provided by Johns Hopkins University. Then we used main geopolitical factors of each country, like income, population metric, climate, and so on. This we took from the World Bank. We also used population mobility data collected by Google. And finally, we used the data on policies and containment measures that were implemented in every country by the government. Next slide. Yeah, so we started by analyzing how socioeconomic factors correlate with the COVID-19 rates. For that, we looked in total of 182 countries at their GDP, GDP per capita, population size and density, as well as average yearly temperature, so climate. As it turned out, factors like the size of the economy or even population density are only loosely correlated with the COVID-19 rates, which essentially means that the virus doesn't choose. The one exception is the average yearly temperature. So the warmer the climate, it seems the slightly lower the mortality rate of COVID-19 is. And this result is consistent with the empirical observations by doctors around the world. Next slide. So overall, though, socioeconomic factors alone do not explain why some countries handle the pandemic much more efficiently than the other ones. And so there must be other factors which are much more important. We hypothesize that the success of handling the COVID pandemic lies in the proactive measures taken by each country and government. In a sense, it's a very optimistic hypothesis because it means everything is in our hands. And this is what we checked. Next slide. So we were in the next step of our analysis, looking at the policies and containment measures that were implemented in each particular country, focusing now only on the European region. Among these policies were school and workplace closure, public events cancellation, restriction on public gatherings, restriction on international travel, stay-at-home measures like lockdowns, as well as contact tracing and large-scale testing.
Yes, so in order to determine which models should we select and look at first, and what would be the best or optimal parameters for such models, we ran a bunch of statistical tests. So first, we looked at the seasonal and trend decomposition of our time series variables that included mobility data, confirmed cases, as well as the enforcement of different policies. And the combined enforcement of policies. So next we tested if these variables influence each other and what kind of impact they have on each other, also if they are co-integrated. Our next step was to check the correlation between the lagged observation of those term variables. That's why we analyzed autocorrelation and partial autocorrelation. And lastly, we ran the stationarity test to check if our data is stationary or non-stationary, which also helped us to choose the best model to look at first. So this resulted in us going for Sarimax, VCM, and random forests. So the plot that you can see on the left side shows the compared true versus predicted values for the number of cases in the UK based on grocery and pharmacy mobility data generated by the VCM model. After further analysis of residuals for this model, we found out that they don't store any pattern, and we were able to achieve fine performance.
Okay, and now I will tell you more about our random forest analysis. So we chose random forests because they were shown before to outperform the usual models such as ARIMA when applied to dataset from the avian influenza in Egypt a few years ago. So that gave us a lot of hope that that's actually a good model to use to predict COVID-19 cases. So we built the model by taking the lagging mobility and policy data combined 2, 3, and 4 weeks ago and predicted the rise in the number of COVID-19 cases. So in the middle plot on the slide, you can see the random forest trained on the UK data, and you can see that it predicts the trend really well, despite not complete stationarity of the data, and it only overestimates the number of cases at the very end. So we were really happy with this performance. And while the most significant factors of this model varied from country to country, we found that the most common factors were the mobility in residential area, in retail places, in workplaces, together with a few policies such as a ban of public events and gatherings, as well as school and workplace closure.
So now our cherry on the top. So here you can see the chart that demonstrates how our models were able to predict what will happen given if the C3 cancelling public events policy is enforced or not. So the blue line show you the number of cases if you don't enforce the measure in the UK. And then the red one shows you what would happen if you enforce the measure. So you can see that without enforcement, the number of cases is actually drastically rising. And then when you enforce the measure, it's actually flattened.
Yes, so our statistical analysis and machine learning models have shown that the mobility data around public and residential areas greatly impact the number of COVID-19 cases. So if we are able to reduce the national mobility, in addition to certain governmental policies, we can really deaccelerate the spread of the virus. So to conclude, we learned a lot from this project. To start with, in the contrary to our initial assumptions, we found out that population and socioeconomic factors do not play a key role in the number of COVID cases in different countries. And using statistical analysis and machine learning techniques, we were able to identify the effect of governmental policies on the mobility and then of the mobility on the number of cases. And we identified that the most common factors were ban of public events and public gatherings, as well as school closure and workplace closure. And finally, and most importantly, we were able to build a framework for a strategy recommendation, which could later be used to advise the governments which policies would work best for their countries.
And that concludes our presentation. Thank you for your time, and we're going to open this up to Q&A.
Thank you so much, Team 8. Really impressive analysis, and I loved how you both just performed the analysis, but also tied it to some important recommendations. So that was fantastic. Up next, we will have team number 15. Team 15 has a very different but really fun project. They analyzed comparative product reviews on table tennis rubbers. And I'm happy to introduce team lead Winnie Young. Take it away, Winnie.
We'll be talking about comparative product reviews on table tennis rubbers. And so before I delve into the details of what our project is about, I'd first like to provide some motivation on why we're interested in comparative product reviews, or what we even mean by that. So if you're like me and have been online shopping, you've probably seen comparison tables such as this one comparing a Borealis backpack and a Jester backpack side by side, and listing some specs head to head, and sometimes also listing out the pros and cons of each individual product separately. Now, what if you were interested in something a little bit more subjective? So for example, which one is more comfortable, or which one of these two backpacks is better for school? And for questions like these, it would be really nice to have someone who has had experience with both products to provide a direct comparison so that it's within the same frame of reference. And so for questions like these, you often might find a simple table such as this one doesn't quite suffice. And you might find yourself, Googling Jester versus Borealis, and up comes a lot of product reviews, and you get buried into a mountain of these product reviews and try to get all the information you want to make a decision. And by the end of it, you might wonder, wouldn't it be great if a computer could just synthesize all this information for us? And if you think about it, this is good for us both as consumers to help facilitate the decision-making process. And also from the perspective of retailers, it would be nice to know what aspects of your products are being compared with competitors and how they fare against each other. So with this motivation in mind, we set out to leverage NLP techniques to mine comparative comments from online forums and product reviews. So just to frame the problem a little bit more concretely, what do we mean by a comparative comment? So a comparative comment is one such as A is better than B for X, whereas a sentence like A is good for X is not comparative. So our goal is that we want to be able to identify the sentences that are comparative in nature, and then to extract the comparative information from these sentences. And our product of choice is table tennis rubbers, which are sheets of rubber that go on a table tennis paddle. For one, because 2 members of our team are table tennis fanatics, and table tennis is awesome. But also, if you think about table tennis equipment, or even just sports equipment in general, there are a lot of choices, and there aren't very many specs that would tell you how a particular equipment would feel like for a certain kind of player. So it's a highly subjective process. And these comparative opinions that you would find in forums are really informative. And to the best of our knowledge, nothing of this kind, namely comparative opinion mining on table tennis equipment, really exists out there. In fact, after we started, we realized that it's comparative opinion mining in general is quite an underexplored territory. So Pooja will talk a little bit about our approach.
So for the approach, there are 4 steps, as we can see in the flowchart, like data collection, data pre-processing, classification of comparative sentences, and information retrieval and visualization. So firstly, we have scraped around 16,000 forum discussions, threads over the million sentence. And then we have performed data cleaning, pre-processing, exploratory data analysis. Then we have classified threads, whether if it is comparable or not. And then we have performed the information retrieval process. So in the last, we have aggregated all the results and visualized it using Dash and Plotly. So as we can see in the table, we have used various tools for programming, backend and front end. Next slide, please. So after data pre-processing, we have done classification on threads and checked whether if it is comparable or not. And for the classification task, we have used Roberta, which is robustly optimized BERT's pre-training approach, and it is a deep learning neural network NLP model. So this model builds on language masking strategy, where the system learns to predict intentionally hidden section of text. And using Roberta model, we were able to classify text in 3 classes, like which is comparative, descriptive, and irrelevant class. We have trained our model with 12 epochs and got around 90% accuracy on training set. As we can see in the plots, there is accuracy and training loss plot, which tells us after every epoch, accuracy is increasing and loss is reducing. And in the prediction, if we give a string to the model is able to predict its class. For example, as shown, so for this specific sentence, model is able to predict the class as comparative with a scale of 99%. So using the Roberta classification, we are able to distinguish comparative sentences from other sentences across all the 16,000 threads, and which narrows down to a smaller subset and pass it downstream for the task of information retrieval. Now Jesse will take over from here.
Right. So after we have identified a sentence as being comparative in nature, we want to extract that information from it. And so the first step is to be able to identify the entities that are being compared in a sentence. So here, TO5 and Barracuda are actually abbreviations that people refer to these 2 rubbers colloquially. So we need to be able to identify those. And we do that by building a dictionary of all possible abbreviations that people would have for various rubbers out there. And after we have identified the entities, we want to know what aspect is being compared. And so for that, we did topic modeling on all these comparative sentences to identify 10 different aspects that are pertinent to table tennis rubbers that people are interested in. And along with each of these aspects, we associate words that people use to describe them. So for example, for the aspect tackiness, people would describe it as being tacky, as being grippy, or being sticky. And along with it, we associate their comparative counterparts. So tackier or not as tacky, so on and so forth. And using this rule-based approach, we can identify the aspect and the comparative word that is used in the sentence. And so after these are identified, we need to actually build the relation, which is the comparison direction. So in this, we also use a simple rule-based approach where we just take the entity that is immediately predecessing the comparative word to be the subject of interest. So in this sentence, we would extract the information that for tackiness, butterfly Tenergy 05 is greater than Donic barracuda. And so we can do this for various, for all the threads that or all the comments that we have identified as comparative, and accumulate that into a database where a front end can then query. And so for front end, we made a dashboard to visualize the data, which Charlotte will tell you a bit about.
So we are very thrilled to show you this live dashboard that we built that we can look at and help users compare results. So let's choose the first rubber product and the second one. Those are Tenergy 05 and Evolution MXP. And if we look here, we can see the results from the online forum opinion mining with all the aspects of comparison and the preference of users. And actually, to the right, we can see all the comments that we mined. MXP and TO5 are short names of the products, and we matched these with the actual name using our self-built dictionary. And here, for more quantitative results, we have also scraped our user ratings of each product. And Evolution MXP here, for example, is faster than Tenergy 05, which makes sense with our review mining. And we also have some word clouds to visualize the results with the most common words. And if we see here, Tenergy 05 is mentioned about its hardness and control, while Evolution MXP is famous for its speed. So this is a live dashboard that can help user both quantify and visualize the comparison aspects of each product and help them choose between the products of their choice.
Yeah, so that's all we've got. We would like to thank our mentor, Dioanne, and our TA, Helen Chu.
Fantastic. Thank you so much, Team 15. That was great. Up next is Team 22, who explored the relationship between housing conditions and mobility, along with COVID-19 across California counties. Team 22 is led by Elizabeth Hawking. Elizabeth, the floor is yours.
Thank you. Sorry, I'm starting my video. So we were working on a project with Measure of America to depict more of a portrait of the state of California and the relationships between demographics, housing conditions, and mobility, and how it relates to COVID-19 across various California counties. So our team is men, myself, Elizabeth, Christina, Chinure, and Xuan. We have a very diverse team, and it was really fun to get to know the girls throughout this project. I'll be talking about our business problem and our impact, as well as some data sets that we used and methodologies, where the rest of my team will talking about the results of our findings. So we really wanted to understand the relationships between housing, COVID-19 rates, and mobility in order to identify specific geographic priority areas and racial, ethnic, and resource inequities within the state of California. And what a result is we want to be able to provide data for action to policymakers, activists, government, and foundations to identify these key counties. Some of our data sets that we use with a census data set to get our population information, race and ethnicity, and our housing data. We also use COVID-19 data set to get our daily COVID rates, such as our death rates. And then we also use Google Mobility Report, and that allows us to capture the change in movement that people in California displayed in comparison to the baseline in January and February of this year. So some key methodology that you'll see throughout the rest of our presentation is exploratory data analysis for variable distribution and ranking, as well as GIS, geospatial analysis, heat map and hotspot analysis, and Pearson correlation coefficients. I'll kick it off to Christina to talk about COVID-19 across the different California counties.
We'll start with race and ethnicity. One thing we learned from very early on is that California counties are very diverse and they vary quite a bit in terms of population as well as race and ethnicity makeups. And when you map it against the number of COVID deaths per 100,000 people in each county, you can see a pretty clear pattern here on the left that counties that are majority non-white tend to have a higher COVID death rate than the counties that are majority white. And in fact, if you look at top 10 counties in California that had the highest number of COVID deaths, you can see that 9 out of those 10 counties were majority non-white. And next, Shuang will tell you a little bit more about different housing conditions and their relationship with COVID death.
Okay, so we select 6 variables from the dataset and decided to use persons per household and median household income as significant variables in our study. This map shows us persons per household in California. Research have shown that 70 to 80% of infections are actually happening within household itself. From this map, we can see a spatial difference between north and south part of the state, where south has higher values in persons per household. Also, inland and coastal are different. Mapping also tells us something we cannot easily find. For example, apart from our traditional perceptions where San Francisco and LA should have higher density, counties such as San Bernardino has really high value. Our mentor has pointed out that this is an area called Inland Empire, which has a lot of farms and the population is fast growing due to new immigrants. The Wall Street Journal has also reported that farmers are essential workers, but they are most affected under COVID-19 in California. If we compare the previous map to the governmental COVID-19 risk map, we can see a similar trend. The southern part of the state is categorized as widely spread. So this is a Coroplus map showing median household income. A Coroplus map shows values from high to low in gradient colors. We can see high income cluster around San Francisco Bay Area, which is not surprising, but the problem is that our eye tends to focus on darker colors or higher values. So we also use hot cold spot analysis, which is a geospatial tool in ArcGIS. This tool tells us statistically significant areas that are not happening due to spatial randomness. Here we notice the hot spot in the state, the north and east part, which is not obvious in the previous map. Those low median household income areas may have limited resources and may be more vulnerable to external shocks. And next, we will move on to mobility study.
So for the mobility data from Google, we have 5 categories and a bigger category called away from home include them all. And to relate it to the COVID data, which is the new death rate data, we apply the 1 month lag, which means, for example, we compare today's mobility data change with the new death rate data 1 month later. And there's 3 important days during the past few months. The first one is when the California government ordered the statewide lockdown policy and when the policy take effect. And the other 2 is the observed holiday. We can see in the right graph here, during those 2 holidays, there's a jump for people to go out more often. And next, we will show you a demo video of our Tableau dashboard. So this page is the statewide, state level data for California COVID data, the mobility data, and we can see there's a huge drop except for groceries start from March. We think the exception for groceries is because it's kind of essential activities for people. And also we can see that there's start from April, we can see people goes to park more often because it's function like a kind of compensation to people for their long hours staying at home. And also we can see for other 3 categories, the levels they are really low. And next we'll look into the county level data. So here we take San Francisco as an example. We can see the county level data, the mobility all stay at low level, but compared to this county, the data is more extreme. which means partly the reason maybe people don't pay much attention because the lower cumulative death rate in this county, but other part maybe it's just people have more other essential jobs they need to go out. And also the 1 month lag correlation we mentioned before, we saw a significant relationship between the movement and the new death rate in the recreation and also workspace and also the stay at home data. But we just say insignificant relationship between the transit stations and the new death rate. And we need to remember that the correlation doesn't mean the causality. So the policymaker may consider this, but there are other underlying impact that we don't have access to those data.
Thank you, Meg. So we'll start with a summary of the key points. Next slide, please. So the key points are simply that there is huge racial disparities. For instance, there are a majority of the non-white counties, that is 18 out of 58, they showed higher COVID-19 deaths compared to white dense counties. Also, there was housing and income disparities, in particularly higher persons per household and low median household income were associated with higher COVID-19 death rates. Finally, mobile disparities was present. Mobility disparities were present. For instance, higher residential usage and higher park usage was associated with lower COVID-19 rates. So this simply shows that across these three measures, it is clear that disparities are present, particularly in the metropolitan counties at the southern parts of California, because these counties are reporting lower death rates compared to others. Therefore, this mandates a call of action in order to reduce these disparities and prevent dark consequences in the future. So this call of action is spaced across three main stakeholders: the policymakers, researchers, and advocates. So the policymakers should incorporate more structured public health preparedness, and also they should ensure that there is strategic distribution of medical and preventive resources. Also, the researchers should endeavor to provide evidence-based research that would explain these discrepancies and provide strategic suggestions to policy makers. And finally, advocates like ourselves, we have to proactively work with policymakers in order to address these discrepancies and tailor efforts based on unique counties' characteristics. So in the words of William Dean Orwell's, inequality is dear to the American heart as liberty itself. Therefore, we should act as advocates to reduce these disparities. Thank you. And before we end this, we want to acknowledge the Correlation One team and the staff and the sponsors, and also our mentor and my team themselves were very lovely. And thank you for this opportunity to present.
Fantastic. Well, thank you so much, Team 22. That was a really amazing presentation. Up next will be Team 28. Team 28 worked with Lyft to analyze driver trends and understand driver lifetime values and churn factors. Team 28 was led by Rehab Rabai. Rehab, please feel free to share your screen.
Hi, everyone. Good afternoon. Thanks, Andrew, for giving us this opportunity. This is Kritika here. I'm going to presenting my team over here, Kanika, Daisy, Lisa, and Rehab. We worked on the Lyft project. The title has Ready to Drive, lifting the driver lifetime value and reducing churn. Moving on to the next slide. The agenda is we'll be going over the problem statement, the data set, exploratory analysis, and the modeling approaches that we used for clustering, segmentation, churn model, and concluding it with experimental design and the business impact. Moving on to the next slide. Why is it very important for Lyft to maintain its 2 million drivers so happy? It's of threefold: because of the driver acquisition cost, the competitive landscape, and the constantly rising demand. We need the right amount of drivers to be present to meet the demand. Moving on to the next slide. The problem statement. We're going to be looking at how to calculate the driver's lifetime value, identify key features influencing their churn and lifetime value, recommend right approaches for the business to increase that, and design an experiment to evaluate whether the recommended approaches are effective. Moving on to the next slide. We were presented with 3 tables, one about the drivers with their onboarded date, and another about the drives that they have taken. It gives us the ride duration, the distance, and the percentage of prime time. And then finally, with the right timestamps, it gives us 5 kinds of events, which says when they requested it, when they accepted it, when they arrived, when they picked, and when they dropped it off. So moving on to the next slide, we did perform feature engineering to identify the features that is more important in helping us calculating the LTV, which is the lifetime value, and the churn rate. So some of them peaked over here: our total number of rides, the median ride distance, whether they are full-time or part-time, the percentage of ride prime time, and the proportion was whether weekend or weekdays. Moving on to the next slide, I'll be passing it on to Lisa to talk about the exploratory data analysis.
During the exploratory analysis, one useful metric we calculated was ride intervals, or the time differences in days between a driver's sequences of rides. We removed ride intervals of zeros because these represent rides within the same day and do not inform us about how many days a driver typically takes before driving again. The left figure shows that most ride intervals are between 1 to 4 days, and that anything beyond 10 days is rare. So maybe a ride interval of 10 days or more could be a definition of churn. When we're looking at the distribution of max ride interval per driver, the right plot indicates that around 50% of drivers have a max ride interval of 10 days or more in the observed data. This tells us that many drivers will take a ride interval of around 10 days before coming back to continue driving for Lyft. So using a fixed interval to determine churn may not be the best idea. This could be more well explained when looking at the ride intervals of some example individual drivers in the next slide. We can see that for the first driver, the maximum ride interval is 8 days, but the driver came back after 2 peaks. For the second driver, we see a periodic trend in the ride interval where it peaks at around 14 days each. This could indicate a driver with tendency to drive on a bi-weekly basis. For these 2 drivers, it might not be the best idea to label them as churn. However, the last plot shows a driver that has not driven for about a month, and this driver could be labeled as churned. Now looking at the drivers in groups based on onboarded date. All the drivers have given at least 1 ride during the month they onboarded. You can see that over 90% of them continue to drive in the second month, shown in the second column of the plot. Overall, we see a high retention on the Lyft platform, but some drivers are more profitable to Lyft than others, and this is investigated via LTV modeling.
Not all drivers are equally important to Lyft. Some will generate higher profit. And so we perform LTV analysis so that Lyft can, for example, distinguish active from inactive drivers, generate ride forecast of individual driver, and predict ride volume for the entire driver database. And we first perform RFM analysis, which basically groups drivers based on how recently, how often, and how many rides they have provided. Then we fit a model using the beta geometric negative binomial framework to the data in order to capture the flow of the rides over time. In the next slide, we show a plot of the frequency recency matrix of our drivers. In the y-axis, you can see how recent drivers have provided rides. So in the lower region, it shows those who have provided rides recently, whereas in the upper region, it shows those who have provided rides a long time ago. Whereas the x-axis show how frequently drivers have provided rides. For drivers in the bottom right corner, these are the best drivers because they drove recently and also frequently. So we find a higher expected number of rides in the projected timescale, as shown by the brighter color. For drivers that are shown in the upper right corner region, they provide rides frequently, but not very recently. And so the expected number of rides that they will be providing in the projected time frame is low. And similarly, we can look at the probability that such driver is still active over some projected timescale, as shown in the plot on right. For example, a driver in the lower right corner who have given rides recently are most likely still active, whereas those who have given rides a lot but not recently in the upper right corner are likely to have dropped out. So the more that they have given rides in the past, the more likely that they have dropped out. And so you can see this curve in the color. And given a driver's ride history, we can calculate the probability of being alive as a function of time for each individual driver. Here's an example for a low LTV driver. They gave a few rides in the end of March after they onboarded, and they did not provide more rides until the end of April. And so we can see that they're mostly inactive, as you can see in this blue curve dropping off. This plot also demonstrates the need for building a dynamic churn model where drivers may appear to be churning or not, depending on when you look at the data.
And then we perform the clustering analysis to segment the drivers into different categories. So if you look at the cluster number 0, you see the performance is the best. They have the highest ride duration, highest total earnings, and highest ride count. So that indirectly gives the lowest drivers that got churned to be present in that cluster. Whereas the cluster number 3, you see the lowest ride duration, lowest earnings, and lowest ride count, and the drivers present in that cluster gets churned highly. So whereas the cluster 2 has an average performance and the churn rate is 50%. So that's how it goes. But one of the key points that ties the story together, if you see in the cluster 0, at least 10% prime time is applied on all the rides, which means they have higher earnings. Whereas in the cluster 3, you see that minimum 31 rides were without prime time, which means their earnings were super low. We use k-means clustering to identify this. Moving on to the next slide, based on this cluster analysis, we were able to segment the drivers into different categories. So if you see the analysis over here, we are visualized using the principal component analysis to reduce the features and in a 3-dimension. So this will be useful for the business so they can roll out the right amount of proportion based on the driver's performance and to keep them and retire. Moving on to the next. I'll pass it on to Kanika to talk about it.
Yeah. So as we saw in the previous EDAs, an average rider activity, it lasts for about 14 to 10 days before churning out temporarily. So we decided to capture driver's activity after every 2 weeks, taking that as a reference point, and compared it with his activity 2 weeks before the reference point till the start of his onboarding week. Hence, in the churn model, any driver who did not give a single ride after the reference point was labeled as churn. Like I said, the reference point was taken after every 2 weeks. This way, we were able to compare week over week differences and tried to understand what might have changed in recent weeks when the driver churned. Some of the important features which were consistent in any of the models we tried included % weekend rides, % weekday 8 a.m. to 5 p.m. rides, tenure on the platform, average earn per hour, earn per week, and also the % difference in earn per week from recent weeks to the weeks before the reference week, the median ride duration and the ride distance. The training data was the rider's activity from week 13 to week 21, and the out of sample test data was a driver's activity for the reference week 23. Moving on to the next slide. We tried multiple models like logistic regression, random forest, gradient boosting, and the final model that was selected was after hyperparameter tuning, handling class imbalance. We also did a regularization in the logistic regression to reduce overfitting. As we can see, all the models, they have the similar F1 score, and the precision was a little higher for the logistic regression. This is majorly because we only had like 837 drivers, and there was a huge class imbalance for the churn drivers. So taking insights from the cluster analysis and the churn model, we created an experimental design, which Rehab will walk through in the next slide.
So based on the findings from the churn model, we found earnings per ride and per hour to be significant features. Thus, we designed an experiment which aims to test whether a modified feature could increase earnings and reduce driver churn. The feature change would involve increasing the default tip shown to riders from 15% to 20%. The control group would consist of randomly selected drivers whose riders receive the 15% tipping screen, whereas the treatment would receive the 20%. The null hypothesis would be that there would be no difference in driver churn between control and treatment groups, whereas the alternate hypothesis is that there is a significant difference. This experiment is cost-effective to lift because if the feature change works as expected, the increased earnings for the driver would come from the rider's pocket rather than Lyft's. However, it does run the risk of riders perceiving the rides to be too expensive. Thus, some important guardrail metrics to keep in mind are daily active users and daily number of rides. After running the experiment, we can use the data to determine whether this feature change does indeed increase earnings and reduce churn, and even segment the results based on the clusters identified earlier to see if particular types of drivers are more sensitive to earning increases. To conclude, we review the business impact of our project. We saw that not all drivers are created equal. LTV modeling and clustering analysis identified those high-value drivers, cluster 0, that Lyft should reward and focus on retaining. The churn model we developed flags drivers at risk of churning, who can be targeted with incentives. And finally, we designed a feature change to reduce driver churn, along with an experiment to test it. And that concludes our presentation. Thank you all for listening.
Fantastic. Well, thank you so much, Team 28. Up next, we have Team 31, who explored the intersection of public health risks, income disparity, and seismic hazard in the San Francisco Bay Area. Team 31 was led by Ben Lin. Ben, feel free to introduce your team and begin the screen share.
Okay, hi, good afternoon, everyone. My teammates Ben, Shiran, Natasha, and I are so excited to be here today and to be presenting our project to you all. It's called The City Dweller at the Crossroads. My name is Athena, and I will be introducing and discussing the objectives and the motivations behind our research. So, from the start, we were motivated by the reality that urban environments expose millions of people to numerous interactions with health hazards, from high concentration of pollutants to socioeconomic disparities to natural disasters. Cities are the crossroads where diverse threats to the public's well-being play out across various and densely populated communities. With this in mind, we set out to analyze how different hazards play out across diverse demographic groups in the Bay Area of California. In particular, we also investigate how seemingly non-related risks influence one another. We focus on pollution risks to air and water, socioeconomic disparities, and seismic hazard. Our core dataset is the California Communities Environmental Health Screening Tool, a rich dataset of diverse environmental and socioeconomic disadvantages that threaten communities across California. To name a few, these variables include the annual mean concentrations of various pollutants, such as ozone, diesel fuel, percentage of children born at low birth weight, linguistic isolations, and unemployment rates. The distributions of several of these are visualized on the right-hand side of the slide. The next dataset is the California Health Atlas, which has a specific focus on medical and disease-related variables, such as diabetes, heart disease, and high cholesterol. Third, we have the Social Explorer database, from which we've gathered bracketed and per capita income values. Lastly, we'll have seismic hazard maps for San Francisco proper from the U.S. Geological Survey. These maps visualize the maximum acceleration the ground is expected to experience at a given location during an earthquake. And with that, I will pass it on to Shiran.
Thanks, Athena. Since we are interested in the relationships between the environmental and socioeconomic factors across census-tract areas in the Bay Area, after looking at some exploratory visualizations and summary statistics of our data, we started with this spatial correlation analysis. We focused on two types of spatial correlation analysis. The first one is the spatial autocorrelation analysis, which analyzes the relationship between spatial similarity and attribute similarity for a single variable. We tested for the global autocorrelation statistic using Moran statistic. If we reject the null hypothesis that the variable is at complete spatial randomness, we can see that the pattern of that variable is correlated to its spatial location. And for most of the environmental and socioeconomic variables we analyzed, including income level, unemployment, ozone, pollution burden, and seismic risks, they all show some level of statistically significant spatial autocorrelation. We use local Moran statistic I as local indicator of spatial association, and we show our autocorrelation analysis results in Moran scatter plots as shown here. For example, here is the analysis for the pollution burden variable. We then distinguished each of the four specific types of local spatial association reflected in the four quadrants of the Moran scatter plot and produces the hotspot and cold spot maps. The hotspot and cold spot analysis is useful in evidence-based policy development and implementation. Another correlation analysis we look at is the spatial cross-correlation analysis. It reviews the importance of the part of correlation between two variables played by spatial relationships, and therefore implements the spatial autocorrelation analysis on a single variable. We use the spatial cross-correlation index and use a dual cross-correlation scatter plots to visualize the correlation relationships. For example, here is analysis for the diesel PM and impaired water body variable. Each of the dual scatter plots put the special points into 4 types by the quadrants of the Cartesian coordinate system. So in this way, we are able to categorize our areas into different types based on the relationship between an area and its neighbors. For example, the first quadrant contains all high types, meaning that an area and its neighbors are both at higher level in this vector. And by combining the local spatial or cross-correlation indices of 2 variables into 1 scatter plot, we will be able to rearrange and further support the clustering result from the dual cross-correlation scatter plots. We examine the pairwise spatial cross-correlation between all variables. Areas falling in the same quadrant or closer to each other in the coordinate system for a specific pair of variables share more spatial similarity among their patterns between those 2 variables. And with that, I'll pass it on to Bing to talk more about our modeling.
So for our final analysis, we want to understand the interplay between pollution and socioeconomic factors on health beyond pairwise associations. So using the 12 health outcomes from the Health Atlas, we combine these measures into a single outcome using principal components analysis to construct a naive measure of disease burden. And using a spatial regression technique called geographically weighted regression that allows predictors to vary over space, we can examine local associations between environmental and socioeconomic predictors on disease burden. Now I'll pass it on to Natasha for our final conclusions and future work.
Thank you, Bin. In conclusion, I'd like to highlight some of our key takeaways from these analyses. Overall, we find that the distributions of many environmental and socioeconomic factors are spatially non-random. First, leveraging geographically weighted regression allows us to conclude that different regions in the Bay Area are affected by strikingly different factors. For example, we can look at predictors associated with disease burden. On the left in purple, across southern Solano County and numerous census tracts in San Francisco proper, we can see that poverty is highly associated with disease burden. However, poverty is not a predictor for disease burden in West Santa Clara County, San Mateo County, or the Palo Alto area. Second, in blue, we observe impaired water bodies to be a potentially important indicator for disease burden in the South Bay Area, particularly the greater urban area of San Jose. This indication is not seen in the Northeastern Bay Area or in South Oakland. Third, in green, unemployment and disease burden are more associated in the Northern Bay Area across Napa and Sonoma counties compared to the census tracts in the Southern Bay Area, San Jose, and San Francisco, where the association is low. Using cross-correlation analysis, we spatially grouped census tracts based on similar correlation indices for every pairwise relationship of variables. Visualized here is one example explained by Shiran, showing the key types of relationships between diesel particulate matter concentrations and impaired water body rates. We observe 4 distinct relationships denoted in color. What this means is that we can map out on the census tract scale similar risk relationships for every pair of public health hazards. These mappings have utility for policy initiatives. They can pave the way for collaboration between communities and like groups. Taken together, our results uncover focus areas for addressing cross-cutting health hazards in the Bay Area and highlight the nuanced interplay between risks that may not be obvious on the first order. This study and continuing investigation can yield actionable outcomes. Fine-scale insights on the direct and indirect relationships between risks can inform equally localized policy initiatives and hazard assessments. While these conclusions are exciting first steps, we are aware of limitations to our study. The limitation most relevant to our present outcomes is our creation of the disease burden index using principal component analysis, based on crude prevalence of select chronic conditions. This is an overly basic method of capturing health disparity, as it does not consider other dimensions of disease burden, such as healthy behavior, admission rates, mortality, and non-chronic conditions. Creating a valid index requires expert epidemiological knowledge. Future studies should take this into account. And please see our poster for further discussion of limitations and results. Lastly, we want to express our gratitude to DS4A and its sponsors for organizing this engaging program, and especially to our mentors, Geeta and Maria. You both took so much time out of your busy data science lives to work through this project with us from the start, reading papers on your own, texting us thoughts in the evening hours. We couldn't have done it without your encouragement and support. Thank you.
Fantastic. Thank you so much, Team 31. That was great. Our last presentation of this session will be Team 43. And Team 43 explored venture capital investment in women-owned businesses. Tanika Askew is the Team 43 leader. Tanika, please take it away.
Thank you all for joining us. Like Andrew said, I'm Tanika, and I've had the opportunity to lead an amazing team of data scientists, Sharmeen, Tina, Hema, Lauren, and Shay, to evaluate how women-owned businesses can beat the biased venture capital system. Did you know that women-owned businesses represent 42% of all businesses? They employ 9.4 million workers and generate 1.9 trillion in revenue. Yet, while growing 2 times faster than all businesses nationwide, we only receive 2.8% of venture capital funding, according to industry reports. Our goal is to help women entrepreneurs understand the VC landscape by producing a model to predict success in reaching a VC, while also investigating gender bias and providing recommendations based on the model.
As we began this project, we realized that there were a lot of factors that could not necessarily be quantified. So we decided to split our approach into 2 directions, one being qualitative surveys and one being the quantitative analysis of the datasets that we had. First, we will discuss our qualitative surveys. We interviewed 5 investors and 3 founders of different genders to discuss their experience with funding and biases that exist. We found these surveys as a whole to be very meaningful because during this effort, all participants were extremely engaged and intrigued by our questions and what the data showed for the industry and their firms as well.
After we conducted our surveys, we took the time to reflect on a couple of key points. First, how much do qualitative attributes really matter? In our conversations, our interviewees described how women VCs are more aware when they're speaking to women founders, so inherently they're more invested. If they're not people in positions that look like you or act like you, there's a lack of ability to connect to their background and starting point. It makes the system subjective as opposed to objective. VCs are always looking at a founder's network as well as their success in previous companies and startups. So if you've never had the opportunity to succeed or form close relationships in the first place, it makes it a lot harder for a future venture to also likely succeed. Another question that we looked at is, does having a woman on the VC board affect the company's estimated revenue? According to our conversations, we learned that there are not enough women venture partners. This is a problem because if a product caters towards women, perhaps in the beauty or lifestyle categories, something such as Spanx, women on the VC board can understand its importance and market potential in a way that men may not.
Now for the quantitative analysis, we graciously received access to Crunchbase from a mentor. We extracted data into CSV files and hosted it on a shared Google Drive to provide continuity for everyone. The 3 datasets that we used were sample Crunchbase companies, Crunchbase investors, and Crunchbase 2019 funding rounds. Based on this dataset, we decided that the scope of our project would be the United States in 2019. Now, in order to begin our analysis, we did an initial cleaning and filtering of our data in Python and Tableau. We created Boolean fields for women-led and founded companies so that we could easily filter based on whether a company was women-led or not. We also changed the column estimated revenue range to estimated revenue greater than 1 million, so the column would give a binary result. Finally, we removed fields that were unrelated to our main focus, such as company description, LinkedIn, Facebook, etc. For data modeling, through surveying our data, we found that a many-to-many relationship was needed to successfully evaluate all factors. So we kept this in mind as we continued our analysis.
50.8% of the US population is women and 42% of business owners are women, yet women only make up 11% of investment partners in the US and are only included in 17% of VC deals. In our sample, we found that 7.7% of funding went to women-owned or led businesses. This was actually higher than the industry average because we've included women-led businesses in our analyses. What we found was that there was a disproportionately low number of deals received by women in comparison to men in states like Minnesota, Washington, Texas, Virginia, and Illinois. Even when women estimate their revenues higher, they continue to receive only a small part of the investment. So Texas and Washington, for example, have a large disparity in the number of deals received by women versus men, and almost 1,000% for women who raised less than 500 million. Because VCs overlook the opportunity to invest in women, they're missing out on so much potential profit. Women generate more revenue while receiving less than half of the funding of men. According to a report by Morgan Stanley, the US Census Bureau's survey of business owners, and the Bureau of Labor Statistics, had the number of women and minority-owned businesses and the portion of revenues matched their percentage in the labor force, gross receipts would have increased to 6.8 trillion, suggesting a missed opportunity of up to 3 trillion for investors. Women-led companies also report 18 to 69% higher profits in the same industries when compared to men.
To prepare our data for modeling, we filled the null values by implementing k-nearest neighbor imputation. Now, our classification model outputs 3 classes: low, moderate, and high, each corresponding to the chance for a women-owned business to get through to the next round of funding. Here we faced the imbalanced class problem. There were way too many low and moderate classes in the dataset. So we had to use SMOT, or synthetic minority oversampling technique, to make sure that we upsample the minority class, which is the high class, before we could go ahead with implementing our model.
For our model, we decided to use a decision tree classification method for better interpretability of the features. The input features we chose for the model are estimated revenue range, the number of investments, and the number of IPO exits. Our output classes are the low, moderate, and high chances of getting to the next round of funding, which we inferred from the funding column of our dataset. So after performing hyperparameter tuning over the depth of the tree, we found our best performing model, which was the random forest classifier. This method constructs a multitude of decision trees at training time and outputs the mode of the classifications. Based on our conversations with various VC investors and founders, these features seemed to be the most important to predict the chance of a business getting to proceed to the next round of a funding. Our results from the model solidify and accept this hypothesis.
After the data analysis combined with the model results, we came up with recommendations to help women entrepreneurs improve their chances of getting VC funds. First, from the visualizations, we noticed states where women receive disproportionately low number of deals compared with men. So we suggest women-owned businesses to set headquarters in states where the ratio is higher, such as California, New Jersey, and New York. States like New Jersey also have startup incubator or accelerator programs. There are also ecosystem building programs such as Female Founders Collective and etc. to help women entrepreneurs build their networks and traction. By doing so, women entrepreneurs will be able to gain a higher amount of funding with a higher probability. In addition to the geographical recommendation, from the order of the decision criteria produced by our tree model, it is really important for women entrepreneurs to confidently and positively estimate their revenues instead of underestimating the expected revenue, especially when they pitch their startups before the VC investors. Last but not least, according to our exploratory data analysis, we realized women-owned businesses with IPOs or investments tend to raise more capital, have more exits, and have a higher probability of receiving additional funds. So for women entrepreneurs who have not generated enough investments or exit opportunities, we recommend them to pitch in the fourth quarter to generate a higher capital raise after passing the Series A funding rounds. Not only women entrepreneurs can beat the buyers by gaining power with themselves, venture capitalists also play key roles in today's diversified world. Thus, we recommend VC firms to diversify the venture partners by adding more women so that they can provide their unique perspectives in funding the new startups. In summary, we are able to conclude that gender disparity in funding does exist, but there are ways for women-owned businesses to increase their VC funding. To improve our work, we will use more data because there is a huge deficit in the availability of data, and there is also a significant amount of null values in many fields. For the next steps, we plan to improve the model so that we can quantify the estimated funding amount instead of classifying them into 3 categories. In that way, we can provide more targeted recommendations for the women-owned businesses.
We developed a live tool for women-owned businesses to use when evaluating where to incorporate and headquarter the businesses, as well as other factors such as how to meet a VC, what time of the year to approach, and where to find VCs and incubator startups and accelerators. For example, after receiving recommendations as a women-owned business, I realized that California is where I would want to incorporate because revenues are higher, as you can see, for data and analytic companies in comparison to New York. The tool would inform me on various decisions like, should I specifically headquarter in San Francisco Bay or should I headquarter in Silicon Valley? What I learned was that Silicon Valley actually received 300% less deals than San Francisco Bay. The tool will also help inform me on various decisions such as various decisions such as the amount of money to estimate for certain industries, what time of the year to raise money for the different locations, the geolocations, as well as where investors are located at in each geographical area. Now, if you have any questions. Thank you.
Thank you so much, Tanika and Team 43. And thanks again for every team that presented, not just in the Top Project Showcase, but at the Project Symposium this morning as well. Just to reiterate, these teams had 4 weeks to prepare these projects. It was a very condensed timeline in addition to their oftentimes schoolwork or professional work. And so we've just been totally blown away by the level of work that was completed here. So thanks again. Congratulations to everybody.
All right, well, we're going to move on to the community awards, and I'd like to introduce, well, basically we are going to introduce the next segment, which is the finale community awards for the top capstone projects. The community awards are determined by our fellows, mentors, and teaching staff. Our Women's Summit team at Correlation One will be presenting the awards. So I'd like to turn it over to Andrew, who will be presenting the first award.
Fantastic. Thank you so much to Polly. Our first award is for data visualization. And so everyone here obviously knows that technical skills are important, but as we communicate our technical findings, particularly to non-technical stakeholders, visualizations really add to the story. And so this award recognizes the team that created the best visual representation of their project. And the award goes to Team 22, A Portrait of California 2020. So congratulations to Team 22. And I'll turn it to Nikia to present the next award.
Great. The next award is for Data Insights, which recognizes the team that uncovered the most interesting data discoveries during their projects. These discoveries may have been a result of interesting data sets they incorporated or the exploratory data analysis process. This award for the best data insight goes to Team 15, Comparative Product Reviews on Table Tennis Rubbers.
Awesome, thank you. So the next award we have up is for real world impact. So one of the biggest challenges in data science and analytics is making sure that the work can actually impact business or social outcomes. Analysis on its own is meaningless unless it can change decisions, policy, or business strategy. The real world impact award goes to the team whose project delivered conclusions which could create actual meaningful changes to our lives. The award for most real world impact goes to Team 8. The effects of containment measures on COVID-19. Now I'll turn it over to Royce for presentation delivery.
Thank you. So the next award is for presentation delivery. The most successful data professionals aren't just data scientists, but they're also data storytellers. They create compelling narratives from their own technical stakeholders. The Presentation Delivery Award goes to the team who created the best data story to explain and articulate their work.
The award for best presentation delivery goes to Team 31, the city dweller at the crossroads.
Yay, I love the sound effects. So we are now at our final award, and our final award goes to the team with the best overall project. The award recognizes impressive achievement across all categories. This project had a real world impact, impressive visualizations, interesting insights, and a strong narrative. So the award for the best capstone project goes to Team 8. I wish I could do something more and dance around here. We're leaving it up to you ladies to defeat this pandemic. But in all seriousness, congratulations to each and every fellow. We are exceptionally proud of the work you've done this fall and look forward for what you are going to achieve. We know that all of you are going to be so successful in whatever you end up doing.